Hi, and welcome to the second video in the series on functions, and in this video we're going to be looking at inverse functions. The first one we looked at a lot of the basics of definitions of range, domain, and what actually makes a function, and this one we're going to concentrate on the inverses. So we dealt with all the grey stuff to begin with, now we're looking at this one, and in particular we're going to extend our knowledge of inverses from GCSE into what this looks like if you start representing these things graphically and how that helps our understanding of functions. So here we go. Inverse of a function, again, something you should be familiar with from GCSE. It basically sends your function back to where it started. Essentially, so I've got a function taking me from my green domain to my range, and that's f of x. Then my inverse function goes back the other way. And there's two things to note. The first thing is this notation, the -1, which hopefully you're familiar with. You've been using that with kind of trig functions for a while now. And secondly, and possibly of a little bit more importance in A-level context, is this idea that if I'm going to reverse my function, then the range of my original function becomes the domain of my inverse function. And similarly, the range of my inverse function is actually the domain of my original function. So those two things swap, and that's a useful thing and useful fact to be able to use when you're answering questions on this topic. Now, the other thing to notice is that if if a function is going to have an inverse, then it's got to be a one-to-one. Because what we've got to be able to do is take a unique value in the domain and map it to a unique value in the range, and then also go back the other way. So take our unique value from our range, that's now the domain of our inverse function, and essentially get back to where we started. So it's only one-to-one functions that actually have an inverse, not many-to-one functions. Right, so if we're going to find an inverse, essentially all we're going to do is reorder the order in which we do any operation. So again, go right back to basics. If I've got f of x is 4x plus 1, I start with my value x, times by 4, add 1, and I get to my new value. And if I go back the other way, I've just got to do the opposite. So I'll start with my value x, take off 1, and then divide by 4, and that gets me back to back to the start. Now, so that gives us the inverse of that function is x minus 1 over 4. Now obviously we don't want to be drawing diagrams like this every time we try and do an inverse. There's got to be a better way of doing it, and as you're probably already aware, the way to do that is essentially just to set y equal to your function and then rearrange it. The y here is just a tool to be able to rearrange against. It's got no other particular significance. So what we're going to do is the same process, but this time in a more mathematical way. So we're going to start with that. So we start with y equals 4x plus 1. And then do the rearranging. There we go. And there you can see already the structure of your inverse. And the final thing that should already have been hammered into your GCSE is that when you write your final result, your inverse function, you've got to write it in terms of x. So we just swap the x and y's back out again. And there we go. F to the minus 1 of x is x minus 1 over 4. Okay, again, hopefully that's stuff you're reasonably familiar with. This is kind of taking it a little step further. If we have a look at the graph, so the red line is y equals f of x, y equals 4x plus 1. The blue line is y equals f to the minus 1 of x, which is x minus 1 over 4. And what we notice from looking at these graphs is that if I draw that line up the middle there, that's y equals x. That green line there is a line of symmetry. Essentially, it's a reflection line, so the red line, if we reflect the red line in this green dotted line, we get the blue line, and vice versa. So graphically, the function and their inverse are reflections of each other in the line y equals x. The other thing to notice is this point here, where the two lines intersect. They're going to meet where f of x equals f to the minus 1 of x. Alternatively, because also that's on our line of symmetry, it's often, rather than setting these two equations equal to each other, it's much easier to set them just equal to x. And that makes that whole job of finding that particular point a whole lot easier. Right, so that's pretty much what you've seen before. This bit down here with the reflections is probably the new bit. Let's just move on and have a look at a question. So we've got 6 parts to deal with in this question. So we've got a function, we're saying g of x, which is x squared plus 6x plus 5. And we've got a restriction on our domain, which is x is equal to greater than minus 3. And you'll notice that the reason that's there will get answered in part D. So here we go. Let's start off with part A, which is just a case of finding some values. So we're saying g of 2, so all we've got to do is put 2 into our function. So that gives me 2 squared plus 6 times 2 plus 5, and we get 21. Fairly simple and straightforward. Part 2, we've got to find the inverse, so we need the inverse of our function, so we're going to start by setting y equal to that. Now, rearranging here is not entirely straightforward, because we can't start moving things over, it just won't work, but there is a technique that we can use to do it, and that is going to be completed square, so that's going to allow us to do the rearranging. So let's do a completed square on that right hand side. So we've got x plus 3 all squared minus 4, and you might just want to take a second just to make sure you're entirely happy with the completed square part of that. And then what we've got to do now is, now we can rearrange it and make it say x equals, so I can do that by moving over the 4, square rooting, and then finally take the 3 off. So there we go, we've got minus 3 plus the square root of y plus 4 equals x. And now finally the final step is just to rewrite that so it's in terms of x. So there we go, we've got g to the minus 1 of x is minus 3 plus the square root of x plus 4. Right, that's part A done, part 1 and 2, sorry, we've just got part 3 to do. So here we go, g to the minus 1 of 21, so we're going to put 21 back into here. So that's minus 3 plus the root of 21 plus 4, so that's minus 3 plus that bit is going to be 5, so that's going to be 2. And you're probably looking at thinking, why the hell has he gone to the trouble of doing that? Because we would have known that, because we'd have appeared g of 2 makes 21, so therefore g of 21 has got to make 2. Sorry, g to the minus 1 of 21 has got to make 2. But I wanted just to kind of do that just to prove that the whole kind of rearranging bit works. So there we go. Right, on to part B. It says find the range of g of x. So if we've got the completed square version of that, which is x plus 3 all squared minus 4, hopefully we know now by now that if we've got it in completed square version, we know that our minimum point on that, if we plot the curve, was going to be at minus 3, because this bit here is going to have to be equal to or greater than 0, and this bracket is going to be 0 when x is minus 3. And if the minimum point is 0, then that just leaves us with the minus 4. So we know that g of x has got to be greater than or equal to minus 4, and that will be the range of g of x. On we go, part C. Let's do some sketching. So there's the curve sketched, and again I've kind of put that minimum point in, so can we use the completed square version to be able to do that, and we've got kind of obviously those 2 points in the steps as well. But because we've got this restricted domain, that means if we're going to sketch the correct version of the function, it means we're going to have that. So we're going to have to basically take out half that curve, and hopefully now that's giving you an idea as to why we've got that restricted domain in place, which we're going to answer in a second. The question asks us to sketch g of x and g to the minus 1 of x. So let's put in our reflection line and now draw the reflection of the red line, which would be that blue line there. And again, you could also do that by looking at it and saying, well, if we had the function of g minus 1x, I'm just going to kind of write it back in because I haven't got it on the screen. So we've got g to the minus 1 of x was minus 3 plus the square root of x plus 4. Then what we've got clearly, you can think about that as a transformation. So we've got our square root curve that looks like that. And then you've got that bit there, which is a transformation that's going to shift it 4 units in that way. And then you've got that bit there, which is then going to shift it down 3 units. So we could have done that as a transformation of the curve as well. Let me just see if I can get rid of my annotations. There we go. Job done. So whichever way you choose to do it, we've got the sketches there. And I've put in those 2 kind of start points just to illustrate that reflection as well. And clearly we've got all 3 lines crossing all at the same point there. Right, on we go to part D. So why is the restriction x equal greater than minus 3 necessary for g to the minus 1 of x to exist? And that goes back to what we said right at the start, which is for an inverse to exist, it's got to be a one-to-one function. And if you imagine if we had this red line and it started going back up again, what we've actually got there would be a many-to-one function, so that we wouldn't have those unique values. So we've got to restrict it so there's only one possible output for every possible input. So it's got to be, for the inverse to exist, the function must be one-to-one, and by restricting the domain, that's what's making it a one-to-one. Okay, right, that's all that. Now it says state the domain of g to the minus 1 of x. If a question ever says state, it's something you can do without any actual working out. And the domain of the inverse function, we said earlier it's going to be exactly the same as the range of the original function. So if we're talking about the range of the original function was g of x was equal to or greater than minus 4, so therefore the domain of our inverse function, what values of x can we have for that? From minus 4 upwards. So that domain has got to be x equal greater than minus 4. And finally, it says solve the equation g of x equals g to the minus 1 of x. So it's where the red line and the blue line cross. So we've got to solve that equation there. But as you can well imagine, if I then had to move that 3 over and then do a load of squaring, we're going to end up with the power 4. It's probably a whole lot easier just to solve that equation there where we just put it equal to x. It's easier to solve that one than it is to solve this one here. So let's just create a little bit of space and solve that equation. Move the x over, whack it into the quadratic formula under our calculator, and we've got two possible values. But we know, because the inverse exists, we know that our original function only has unique values. There's only going to be one possible value. So we're saying, well, which one is going to be the correct value? Well, we're going to have to take that one out because that one is less than minus 3. So it's not in the original domain. That would be a point that would be somewhere down here. If you can see where my mouse is there, you can imagine the two lines would meet again there. But that's outside the domain of our function. The one we want is this one. So that means that one there is our solution. And there we go.